Everyone, we'll look at simple harmonic motion here and see how it relates to the lab you did today. So we had masses on springs that were oscillating back and forth like you see in this picture. In this picture we're going to deal with just one spring and watch how it moves as it goes through its motion. That dotted line there is the equilibrium point. If you pull the spring back from the equilibrium point, it's going to feel a force. That force is going to try and pull it back to its equilibrium point, so I'll put spring force in there. There's obviously gravity and the normal force from the floor. However, those two are canceling out and not contributing to this thing accelerating. So I can just say that the spring force is going to make our mass accelerate. And I know that the spring force is minus kx. So right now this object is going to experience a negative acceleration. If I want to solve for the acceleration, I can divide both sides by m and see that my acceleration is kx over the mass. The reason it's negative is because the spring force is trying to restore you and bring you back to equilibrium. When the mass gets all the way over here and crunches the spring doesn't like that either. The spring's going to try and push back and accelerate it in the positive direction back towards the equilibrium point as well. The acceleration again is going to be kx over m, this time just positive. And since we have an equation for acceleration and a acceleration that depends on the distance, we can say that the acceleration, remember, is the second derivative of our position with respect to time. So we have a second derivative that is equal to minus kx over m for that same variable. And that's what it means to be in simple harmonic motion. The rules for simple harmonic motion are that your accelerations are proportional to your negative displacements. So if you have a negative displacement, you'll have a positive acceleration, or if you have a positive displacement, you'll end up with a negative acceleration. And that's the difference between simple harmonic, or someone brought up in class, a bouncy ball, being periodic motion. So if a bouncy ball could return to its normal height without any frictional forces and bounced up and down, when it does that, it could go back and forth in a time that you could replicate again and again and again. However, the force is caused by gravity, and gravity's force doesn't change in that small of a distance, so the acceleration is constant the whole time that it falls. In this case, the accelerations are going to change based on the spring forces growing and shrinking as you move back and forth in simple harmonic motion. And if I put a marker on that mass as it goes back and forth, it would trace me a line. Or if I had the mass going up and down, it would trace me a vertical line. So if we look at this, what I'm trying to demonstrate here is that my hand is going back and forth at a steady rate. And if I start walking with my hand oscillating at that steady rate, what I create is a wave. And not just any type of wave, it actually looks like one of your mathematical signs you're used to seeing in math class. So let's see which one that actually comes out to. The displacement seems to follow a cosine curve. The curve starts at 1, goes down to 0, goes to -1, back up to 0, and then to +1, which looks exactly like what I've drawn below with that marker and mass on a spring. It's going to be at an amplitude, it's going to come down to that equilibrium point, go to a negative amplitude, and then back up to positive amplitude over and over and over again. So what that tells us is that the mass on a spring was always trying to get restored back to its original location. It's trying to get to the equilibrium point, but there's a problem once it hits there, and we'll talk about that. The maximum amplitude we call A. That's how far you are from the equilibrium point. And if I wanted to write that out and figure out where the object is at any moment in time, I could write that as A times the cosine of theta. So as I go back and forth in my motion, I can see that theta will tell me what my amplitude or my displacement is from equilibrium when I put different thetas in my setup. So like we talked yesterday, with a wheel going in circular motion and trying to relate circular motion to simple harmonic, let's look at that wheel on its edge. With the wheel on its edge, you can see that the marker gets to one end point, whips around in front of you, and gets to the other end point. So it goes back and forth, just like the spring on a mast. You can actually tell when it's moving, when it's not really moving in its back and forth motion. Look at the marker carefully. It'll come right into focus and then disappear as it flies past your face, and then comes back into focus on the other side. So at those two peaks, think of those as the amplitude of the marker going back and forth and back and forth. When they cross right in front of your face or right in front of my face, that's when they've hit the equilibrium point. So we're trying to relate circular motion to simple harmonic, and the reason we want to do that is because of the frequencies. Since angular frequency, or omega, is really what we used to do for angular velocity of a spinning wheel, to figure out how far you go in one circle is 1 theta, which is what we have as a cosine of theta. Since that theta is 2 pi radians to go around once, if I want to find omega, all I have to do is do 2 pi over the time period. But if I don't have the time period and I'm given the frequency in hertz, I can take the frequency in hertz and multiply by 2 pi radians and also get the omega. So what does that let me do? Well, omega is theta over time, and I want to substitute out that theta in my equation. What you end up getting is x equals a cosine omega t plus that little delta there. That delta we call a phase constant, and yes, omega t plus delta must be in radians. So here's the one time your calculators should be in radians to help you figure out exactly where the mass is. Doing it in degrees will not help you whatsoever. So let's analyze something going back and forth in simple harmonic motion and look at its amplitude. So here we have the mass. The mass is at an amplitude away. So at the amplitude, x equals a. This is when time equals 0, and if we were going through our cosine function here, this is when theta equals 0. As the mass rockets back to the equilibrium point, we can now say that my x equals 0 at this point. Well, how in the world can I have no displacement? To have no displacement, since it's a cosine function, I need to be 90 degrees through my oscillation, or in this case, I need to be at a quarter of my oscillation, or a quarter tau. When I reach the far end, my amplitude now becomes negative a. And when I have negative a for my amplitude, that means that I've gone a full half of my oscillation, or a half tau. And when I get to the equilibrium point again, x is going to equal 0 again. Theta at this time is now going to be 3/4 tau. And when I reach the far end again, x is going to equal my amplitude. Everything's back to normal, and we've gone through one full cycle. So when you go through your cycles back and forth here, you can watch where it is, knowing what time you've gone through your oscillation. And again, this follows cosine perfectly. Here's a, here's 0, here's negative a, 0, positive a. Perfect cosine graph for our displacement. And I have mentioned that as we go through this, I've been saying that my thetas have been in terms of tau. What is tau? Tau is simply 2 pi radians. It's kind of an easier way of seeing how this thing goes around the circle. So as you go around one full cycle, yes, your theta does equal 2 pi radians. That means that halfway through the cycle, we are at pi radians, and at a quarter of the cycle, we're at pi over 2. At 3/4 of the cycle, we're at 3 pi over 2. And trying to remember all those little halves and 3/2 might be a little confusing. But if you just talk to it in terms of tau, one full spin is 1 tau. And I'll put a link here for looking at the fight between pi versus tau. So if we were trying to do an example here, let's say that our amplitude is 5 meters, our angular frequency is 1.5 radians per second, and in a time of 2.5 seconds, where is the mass? So if we were going to actually go through and crunch these things out, if I want to find my position at 2.5 seconds, I simply just got to substitute in things that I know. So x equals a, which is 5 meters, times the cosine of omega t, omega being 1.5 radians per second, multiplied by the time that I'm interested in, which is 2.5 seconds. So when you multiply all those out, and again, make sure that 1.5 times 2.5, make sure those are in radians when you do your calculator, and you'll get an x distance of negative 4.1. So if the mass was displaced 5 meters from the equilibrium at time 0, at 2.5 seconds, it's at negative 4.1. The problem with just punching in that equation and figuring out where it is that doesn't tell me the whole story. The object could be at negative 4.1 on the way to the other amplitude or on the way back. So where is that going to be? Well, that's where time, period, and frequency are going to come in. Knowing that omega is 2 pi over t or 2 pi f, I want you to figure out the frequency and the time period here and tell me, is that negative 4.1 going to be on the way back or towards that other amplitude? So what about velocity and acceleration? If there's a displacement for an object in simple harmonic motion, that must mean the object could also have velocity. And we know that velocity is just the derivative of displacement over time. However, the displacement now is that a cosine omega t. So when I write a cosine omega t as my displacement, I now need to take the derivative of that to figure out what the velocity is. And this is not easy now because I'm taking the derivative of x with respect to time, and time is sitting inside this cosine function. So it means we've got to employ the chain rule. It means you got to take the derivative of the inside and multiply by the derivative of the outside. So the inside should be easy. Omega t plus delta. Delta is just a number. Omega t becomes just omega. So omega comes out front, but then I have to multiply that by everything else outside. So the derivative of the outside is a cosine of the omega t. So the derivative of cosine becomes negative sine. So the velocity of an object as it goes through simple harmonic motion, so velocity here becomes omega a multiplied by sine omega t plus delta. So the velocity doesn't follow cosine, displacement follows cosine. Velocity now seems to follow a negative sine graph. Starts at 0 and starts its oscillation. But since it's a negative sine graph, it's going to look like this. So it looks like I'm going to have no velocity in the beginning, no velocity here in the middle, and no velocity here at the end. Let's go back to our picture and identify those locations. My velocity here at the amplitude, I'm at the farthest point, the mass has stopped, so it is not moving whatsoever. As it rockets back towards the equilibrium point, the velocity is now in the negative direction. And then when it gets to its amplitude at the far end, when it gets to negative a, it goes to 0. And then when it gets back to equilibrium, now the velocity is moving in the positive direction. And when we get to the farthest point, the speed goes to 0 again. So since it's following a negative sine curve, let's map that out. We said the velocity was 0, then negative, then 0, then positive, then 0. So the velocity of something in simple harmonic motion follows a sine curve, a negative sine curve based on the directions we picked. What about our max velocity? What would our max velocity end up being? Well, my max velocities occur at these two locations. When I've got my theta equal to 1/4 tau and 3/4 tau. And if you put those 3/4 tau or 1/4 tau into my sine equation, sine of 90 or sine of 270 end up being 1. So that means that this whole equation to that, the maximum velocity of an object in simple harmonic motion is omega times the amplitude. So if you know the angular frequency and you know how far away it is from the amplitude, you've got your maximum speed. And those maximum speeds, remember, occur at equilibrium. So that's a cool thing. Let's do the acceleration. The acceleration is just the derivative of the velocity as a function of time. So that means I got to do chain rule again. So inside, omega t just becomes omega. So on the outside, I get omega squared. And then I have to take the derivative of the outside. So that's a, and the negative sine, the derivative of negative sine comes out to negative cosine for our acceleration. So the acceleration seems to follow a negative cosine curve. Well, what would negative cosine look? Negative cosine would start at -1, go to 0, go to +1, come back to 0, and go back to -1. So let's analyze our three pictures again and determine each of our accelerations and when they occur. Alright, so we are at the far amplitude at time equals 0. We're farthest away from the equilibrium point. The spring is trying to pull the mass back, and that means there's an acceleration in towards the equilibrium point. So the mass rockets towards the equilibrium point, and when we're at equilibrium, the forces cancel. If forces are 0, that means there's no acceleration. And then we get all the way to negative amplitude. The spring compresses. It doesn't want to be compressed, so it's going to send the mass backwards and accelerate in the positive direction. Then we get to equilibrium again. Forces cancel out, and we're back to no acceleration. And when we get to our far point, the spring is stretched. It doesn't want to be stretched, and so it's feeling an acceleration back towards equilibrium. Graphing that out showed me negative acceleration, no acceleration, positive acceleration, no acceleration, and negative acceleration. So an acceleration curve follows the negative cosine. And here are your three graphs for simple harmonic motion. The maximum amplitude for our displacement is A, the maximum velocity is omega times A, and the maximum acceleration is omega squared A. Do your units and make sure that those work out to meters, meters per second, and meters per second squared. So the last thing we want to do with this, how we can calculate the angular frequency of a mass on a spring. Recall from the very beginning that the acceleration of a spring is due to kx over m. And we now know that the maximum acceleration of things in simple harmonic motion is negative a omega squared. So what I can do is I can put those two equations together. So negative a omega squared is the maximum acceleration you experience in simple harmonic motion, and we know the maximum acceleration is due to the negative km times our displacement. Our displacement, though, when we're at the furthest point, is our amplitude. So that's going to take away the minus sign and the amplitude, leaving behind omega squared k over m, which is exactly what we did in lab today. We had to square the angular frequency, get the inverse of mass, and the slope of that line ended up giving us our effective k constant for our simple harmonic motion. So here is how you can calculate the angular frequency of a mass on a spring. All you need is the k constant and the mass, nothing else. If you know how stiff the spring is and how massive that object is on the end, you can figure out how quickly it's going to oscillate back and forth. And if you look, there's no amplitude in that equation. If there's no amplitude, it doesn't matter whether you pull the mass back very far or very short. As long as those have the same mass and the same exact k constant, they will oscillate back and forth in the same exact time. So here's a graph of showing you a small displacement versus a large displacement. They both reach equilibrium at the same time. They both reach amplitude at the same time. However, it is true that the object that has a bigger amplitude will be traveling a faster speed at the equilibrium point. So these are the concepts behind simple harmonic motion. We will analyze this more in our next video with some more examples and analysis from lab.